I'm going to load up the handout in the chat box. Perfect, load it up. Don't mind, going to do the usual, make a someone to be the designated letter inner. And I think, we'll see if this ends up being it. Each time it's been a slightly smaller and smaller number, so I'm assuming you were the dedicated diehards. So one thing is just the feedback I'm getting from your votes. Just want to double check. Is translational motion suddenly not such a high priority, considering it's not tested all that much that we could use that differently? That was the latest feedback, and then I'm kind of relieved to see somebody said that. Yeah, okay, perfect. I think it was basically a special interest of a couple people, and I don't see them in the group today, so I don't know. So just, I don't want to railroad somebody's like one request out, but by the same token, I don't want to waste everybody's time on something that's just not that tested. Like something on physics, I guess, that first chapter, but the reality is the second physics book is so much more critical. Waves, fluids, and like light and optics lenses, those have much more applications to bio. Biochem wise, I think AAMC passages, although I flamed out in office hours yesterday on one of them, and like went back and looked at it and like, oh my gosh, that is one that was straight out of CP. I think that would be the best bet for like the applied biochem. Because my biochem is admittedly a little bit on the old side, and from the chem department. I took my biochem as, if you will, chemistry class that had a slight bio component. So it's not as helpful for the MCAT as what you might need, but I can still toss some in. Okay, yeah, so work and energy. In the nuclear, I was glad to see somebody put that in there, because for whatever reason, nuclear has a tendency to show up, a propensity to have a few things here and there, and it definitely ties into medicine. Okay, so I think actually most everybody's going to be here is here. So load up the handout one more time, and hopefully it's coming across nicely. And then I'll go ahead and get started on this. Waves definitely have to be studied. So one thing that I would highly suggest when it comes to waves, just keep a real simple fundamental idea that when a wave interacts with an interface between two media, so in other words, let's say it goes air to water, air to solid, air to tissue, water to tissue, whatever the interaction is, at every interface, a few things can happen. Number one, can waves reflect? Yep, so they can definitely reflect. Can they refract? Go into a new medium? Sure, the change speed, and depending on the angle of propagation and the speed difference, it'll also change its trajectory, so you can get refracted angle. Can it potentially be absorbed? And can it potentially be emitted? Absorbed and re-emitted in a different way. So every single one of those can be used in some fashion to image within a biological system. So is there any technique you can think of where we specifically target light, target a focused collimated beam of light at one specific location, have that point absorb the energy? So is there any biological thought or notion, application, anything you can consider where we target energy in the form of EM photons, or actually any way, but particularly EM photons? Do we ever target that concentrated in one point? Possibly. I'm going to go even more specific than that. Laser surgery. Laser surgery is taking all the rays that are normally going out in all different directions and through a series of mirrors and I guess just the selected pathway, make a very coherent beam going in one direction and target one specific spot. But definitely, how many would agree the absorption process, sending a wave and having it absorbed in one point, but then having it absorb so much energy so fast that it breaks the bonds or destroys the material? Does that seem reasonable? Is that one thing that could be potential in the MCAT, laser surgery or laser targeting? Sure, okay. Do we have anything where we send in waves and see how they interact with the medium? They go into it, so refraction coupled with diffraction. As long as the wavelength is comparable to what we're studying, we get interaction. That would include CT scans, X-rays, excuse me, ultrasound imaging. It's how these waves interact with whatever medium. Reflective-based ones, again, ultrasound, you can basically echolocate something by sending in the right wave. So the key thing is, know as much as you can about different techniques, but don't overdo it. More important to realize that some ways, somehow, it's going to depend on one of four interactions with a wave: reflection, refraction, absorption, emission. Every single medical technique where we employ a wave is taking advantage of one of those. And so that's kind of what today is about, is just what happens with sound waves when they interact with different media. And then we'll also do that with light. So with that in mind, I think everybody's here. So I'll go ahead and get started on this then. So just want to start with the concept of sound. So sound is a longitudinal wave, and want to emphasize the difference between longitudinal or transverse wave and the different behaviors they have. So for instance, let's consider the following picture. Just picking random shapes. There's nothing special about this, but I want to note every single one of these in very specific position to begin with. So I'm going to mark it. Some of these just going to put a little line here to denote where they start. And I want to describe what a longitudinal wave is. So by definition, how many learned that a longitudinal wave is where the displacement of the material is in the same direction, it's parallel with the propagation of the wave? You no doubt read that sentence, and how many of that sentence make absolutely no sense to? The displacement of the material is in the same direction as the propagation of the wave. Okay, so we need to define it differently. I'm still going to say that's the right definition, but instead we're going to say it's a wave where the particles move along with the wave. So they move back and forth, left and right, the wave goes left to right. If they go up and down, the wave goes up and down. It simply means it helps, I'm sorry, reading a chat question. It simply means it moves in the same direction. So in this case, let's take all these particles. So when a wave propagates, is there net movement of matter or just temporary movement of matter, but ultimately it ends up in the same spot? Temporary displaced, it'll be displaced, hit a neighbor, come back, hit a neighbor, but ultimately end up in the same spot. So good for us, because ocean waves, lake waves, do you agree, don't really crawl up on the shore, they stay where they're at. So there's no net movement of matter, but is there movement of energy? So waves propagate energy in some way. Okay, so let's pick any one of these. I'm going to choose this one. And what I mean is these will go left and right. So let's say we give it a bump on this side. Can we propagate a wave? So there it goes. So this one right here, it's moving. Going back, hits again, hits and stops. It ends up in the exact same position it started in, but the wave went from a collision to a collision to a collision to a collision, kind of like a domino effect. Which means, does this type of wave need a medium? Does longitudinal wave require a medium? If one thing has to hit another, hit another, hit another, hit another, absolutely. So this is going to be one of the biggest differences between light and sound. In terms of sound, would you think it's going to make it better or worse for propagation as the particles get closer together? So I have them pretty far apart. If we move them a little bit closer together, would that make it easier or harder for that wave to propagate? Better. They can hit their neighbor and come back to position faster. So the speed of a longitudinal wave, such as a sound wave, depends strictly on how quickly can this particle move over, disturb its neighbor, and then come back to original position. Okay, that's going to be the big ordeal we're dealing with. The faster it can hit its neighbor and come back, the faster it travels. So I'm going to throw just a handful of questions at you, and I want you to zero in on how fast can it hit its neighbor and come back. Which is going to go faster? Speed of sound in a gas or a solid? Okay, this is where it's tricky. In a solid, are they already touching each other? They're already touching. They just hit it, boom, 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 boom. And all it has is vibrate over a little bit and come back. In a gas, it has to move all the way over and come all the way back, all the way over and come all the way back. Speed of sound is actually faster in a solid than a liquid, faster in a liquid than a gas. Okay, second question. Is the speed of sound faster in a lake or the ocean? Perfect. So it's 50-50. We're all over the map. Okay, that is true. Salt is a key thing here. So tell me, what does salt do to the boiling point? If I add salt to a tank of water, a glass of water, addition of salt increases it. It raises the boiling point, it lowers the freezing point. But adding salt to water, it will dissolve in and cling on to water molecules and hold them more tightly. Which means if there's a little bit of salt, if these are water molecules here and there's salt in between, if it gets pushed to the side, is the salt going to pull it back? Is it a stronger force, i.e. the same force that pulls it in and makes it harder to boil, can also pull the water molecules back? It helps restore it. The salt clings to the water more tightly, so it's going to be displaced but come back faster, so it's going to restore to its original position sooner. The speed of water in a lake, depending on around like 25 degrees Celsius, is around 1510 meters per second. In the ocean's around 1540 meters per second. So the salt actually increases the speed of sound. So if you think about it, it raises the boiling point because it is increasing the intermolecular forces. Same story here, it increases the speed of sound because it's increasing the intermolecular forces. Yes, nailed it. So everybody read what Melody just put in the chat. That's exactly right. So it's not so much the volume of how far it's traveling, it's how close are the neighbors. So if I took a massive ocean and a tiny little lake, the water molecules are still doing the same thing. They're still interacting with their neighbors. Just one has salt, one doesn't. Yeah, so it's not the ocean wave itself. It's not the lake wave. It's the sound within it. And it's just, I guess it's just getting used to that thought. The faster it can hit its neighbor and come back, stronger forces, lighter gases, closer together to begin with. All those are going to help. No, it's faster in an ocean than a lake. So it's 1540 in the ocean. It's 1510 in a lake. And what salt does, if I have Na plus and Cl minus, so let's say I have Na, actually, let me make a different color. Actually, let me write more neatly. Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. And I'm just tossing those out in a certain way. Are they going to hold on to the water molecules more tightly or less tightly than water holds onto itself? More tightly. So when one gets pushed away, it's going to get pulled back by the attraction of sodium. When it gets pulled away, it's going to get pulled back by its attraction to chloride. So because ionic bonds, exactly, ionic bonds are stronger. Ion dipole stronger than dipole-dipole. If you knock the water molecule out of place, it's going to come back sooner. It's going to come back because a stronger force pulling it back. 1510 and 1540 are speeds, not times. Oh my gosh, can't write the S. Sorry about that. So the first one is the lake, no salt. 1540 is the salty water, the ocean water. I know that's what I guess it's what it sounds. Yeah. So not so much time, but actual speed, meters per second. Okay. But longitudinal waves, let me just go back to defining that. They go the same direction. So if they move left and right, the wave travels left to right, as opposed to the other type of wave. So when you go to a sporting event, if you actually do, but you're studying, so let's say you have a friend that goes, have you ever heard of them doing something called the wave? Does that ever happen at a sporting event? Okay, so one person's seen it. You read about it in the passage. Okay, so possibly you've heard of this. So I didn't get enough information about how to do this wave, and I was confused because they didn't specify, was I going to do a longitudinal or a transverse wave? So let me ask you about this. In a wave that they do in a stadium with a bunch of people, do you move left and right, or do you stand up and sit down when doing the wave? You go up and down. And the wave goes up and down, or the wave goes left to right? The wave actually goes left to right. So the wave is moving left to right across the stadium, but you're going up and down, meaning the particles are going in the same direction or a perpendicular direction to propagation. Perpendicular. You can actually say fans do the transverse wave. So they go up and down. So if they go up and down, but the wave moves this way. So let's say these are all the particles. Let's say I'm talking about a solid. Here we go. The wave starts out, and it's going to go any second. Oh no. My usual complaint about my Bluetooth. There we go. So finally it's kicking in. So each particle, let me just pick this one for instance. It's going up, comes back down, goes down, and then comes back. Every particle ends up in the same spot, but they're going up and down, but the wave goes left to right. So fans do the transverse wave. Does it make sense what the difference is? These move left and right, the wave goes left and right. These go up and down, but the wave goes left to right. The key thing, the absolutely critical thing you must know is sound is a transverse wave or a longitudinal wave. Longitudinal. Light, EM, is a longitudinal or transverse? Transverse. Here is the major difference that hopefully will clear up. Sound needs to be tightly packed. The faster it can hit its neighbor and come back, the better. So a sound wave travels better in a solid because they're touching already. You don't have to move as far. Than a liquid, and better in a liquid than a gas. Conversely, a light wave has to move the particles all up and down. So would a solid make it harder or easier for it to move along? Harder. So the speed of light is faster in a solid or a gas? Speed of light is faster in a gas. Speed of sound is faster in a solid. So strong forces between particles help sound, hurts light. So are those the same or opposite behavior? Complete opposite behavior. Okay, so something that hopefully helpful. So if that was a solid, if I'm in a liquid, liquid molecules might still be touching, but they move faster. So the speed of that wave, would you say this wave looks a little bit faster than the one I did before? And then taking to an extreme, if all the particles are apart, like a gas, so traveling through a gas, goes much, much faster. Yes, everybody, oh, okay, it was a private message. So someone who has incredible insight to sound insulation. Why do we double pane windows? Excellent point. So basically what you were mentioning is, perfect. It has an air gap between them. Does that help make the soundproofing? Two things that I have going on. Number one, if it's evacuated, sound cannot travel very well. So if you have an air gap between two solids. But the other thing is, a wave easy to transfer from one medium to another, or is it actually harder to or a little bit on the challenging side to transfer a wave. Pretty hard. The bigger the difference in density, the greater the chance of getting reflection. The closer they are in density, the more it's going to transmit. So if you go from a solid to a gas to a solid to a gas to a solid to a gas, it's going to be really hard to transmit. So we have double pane windows because that sound wave is going to go through a solid and suddenly have to transfer to a gas, back to a solid, makes it very inefficient. So really great example of that. If you've ever been on an airplane, they have the cabin, they have the fuselage, and then they have the shell on the outside that has the wings attached. So does that make it pretty much soundproof? How many have ever been inside the jet, sitting in a seat right near the wing, right near the engine, and you really can't hear them? But if you're outside, would you agree the engines are ungodly loud? So they do that by having lots of solid to gas, to solid to gas, solid to gas interfaces. So it's very, very hard to transmit a wave through a changing medium. So you ideally want to transmit through one medium, and for sound, ideally through a solid. So you can definitely verify this. How many have heard their neighbors before? How many live in some sort of student housing where you can definitely hear your neighbors? In fact, anybody have that really generous neighbor? You save all your electricity not having to pay for any music because they share all their music with you 24/7. They're so generous. So I personally never smoked, but I was quite a proficient secondhand smoker because I had so many wonderful neighbors that shared. So think of all the money I save on my tobacco addiction. So, and I mean, being a smartass, but yeah, I mean, secondhand sound travels through a solid. You can definitely hear your neighbors. But how many noticed if you're a few apartments away or a few doors down, it's not as bad? So every time it goes from a wall to the air to the wall to the air to the wall, it loses its intensity. Okay, so again, just want to hang on to the thought that longitudinal wave for sound, transverse wave for light. We're focused on sound today, so I'm just going to do strictly longitudinal waves. Yep, the interface thing applies to both, exactly. Now, reality is it's more dramatic for a longitudinal wave, but it still applies to both, by all means. Okay, so with that in mind, I'll go ahead and get back into this. So a few things you need to know for sound wave, random facts. This equation, how many just know this inside and out? You've had this beaten into you so thoroughly, you'll never forget it. Yeah, I mean, this one is just hopefully programmed in. I like to think of it in terms of my goal to run in the next Olympics. I want to be the fastest person in the world. So if I want to go faster, I have two choices. Number one, can I take more steps per second? Can I do, you ever see the movie The Incredibles? Does Dash run fast because he has long strides? Because he takes a ton of steps per second? So where's his speed coming from? Frequency or wavelength? Tons of steps, high frequency. I don't know if I can do that. So what I'm going to do is I'm going to have leg extensions. My legs right now are roughly 3 feet long. I'm going to make about 10 feet long. So that way, can I take longer strides at the same frequency? Will I go faster? How genius is that? I'm going to just totally win the Olympics. That Italian guy who won it all, he better watch out. Oh, yeah. Always Mr. Negative, Mr. Air Resistance. Oh, fine, I'll make my legs 11 feet long. I'll definitely make the stride so much bigger, I can go faster. So how fast you go depends on how often you step and how long your steps are. Okay, so far so good. Do the units work out? Let's see, cycles cancel, so meters per second, check. Note that this is known as a hertz. So cycles per second is a hertz. And typically wavelength, we just put meters. We don't emphasize the cycle, but technically it is meters per cycle. And I want you to tell me, I want to show one wave. I don't know if I've done it. I think that's what a wave looks like. Is that one wavelength? How many learned that that is one cycle? Goes up, back to the middle, down, back to the middle. Okay. This is, I think, only half a cycle, isn't it? No. So what's that? That's one full cycle. High point to middle to low point to middle to high. You back to the same spot. So if I continue the way like this, keep on going. And then that would also mean, is this also one full wave? Yes. This is where it gets a little funky. When we do waves on strings, we're going to do it like that, from node to node. But when I do waves in a pipe, let's say I have an open pipe, open, open, or if I have an open, close pipe. How many of you have ever seen waves drawn like that? Node to node on a string, or antinode to antinode? Do those seem somewhat familiar? So I have to recognize them in context. But this equation is going to work for any and all waves. For one single cycle, it has a certain length called the wavelength. It's going to go up, come down, and come back. It's going to happen so many times per second. If I combine those two, I'm going to get how fast the wave travels. Okay, pretty happy with this. I'm going to get rid of my picture. They'll show up again towards the end. Clear this. For sound, for whatever reason, they decided to have their own individual words. So how many have heard pitch to describe the frequency? High pitch and low pitch sounds? Okay, so high frequency, low frequency. And then instead of saying amplitude, which also applies to waves in general, we say loudness. Louder sound is high amplitude, quieter sound is lower amplitude. This is important to understand conceptually. The speed of sound depends on how fast molecules can return to their original state. Sound is fastest in a solid, next in a liquid, and slowest in a gas. Yep, so physicists can't spell. How can you say that? Yeah, they come up with their own words, misspell them, and use the wrong first letter. Welcome to physics. Okay, so I have this. And I think this is an okay thing to memorize. I want to be careful saying how much you memorize, but if you have a little more room in there, might as well add those two. Why does it say approximate? Why doesn't it say exact? Lots and lots of variables. Will the temperature affect speed? Sure. Heat it up, molecules move faster, they hit their neighbor and come back sooner. Temperature going up, speed of sound will go up. Will it depend on pressure, at least for a gas? Pressurized gases collide more or less. They collide more, the particles are more compact, so therefore they're going to collide and hit their neighbor and come back sooner. So speed of sound in a gas definitely depends on temperature, so this number can fluctuate. Can it even depend on the molecules themselves? Will speed of sound be different in air that's, let's say, humid, rich with water, as opposed to dry, arid? Definitely. Lots of factors involved. So know these as rough numbers. Do not memorize these exactly. Okay. And then sound is the opposite of light. Just one's a longitudinal wave, one's a transverse wave. If you know light really well, you can fake your way through sound, or vice versa. That said, I'm going to give you two scenarios, and you tell me whether I'm talking about light, sound, or all waves. Number one, you can have a Doppler effect. Is that only for sound, only for light, or all waves? And so we typically only use it for sound when we see it in physics, but reality, it applies to any wave. And somebody typed it in perfect. Blue shift and red shift. So it can apply to light, it can apply to sound. So I'm going to conceptually toss it out here. You tell me what you expect to have happen in these two scenarios, and then we'll see if we can apply it to sound and light individually. You're sitting in your desk, minding your own business, and me being the violent person that I am, decides to pick up these bean bags and start throwing them at you. But I'm also very consistent. I throw one per second. So I throw one, a second later I throw another one, a second later I throw another one. Does it matter how fast I'm throwing them, or is it still going to be one per second? So if I release one, second later release another one, second later release another one, whether I throw them fast or slow, are they still going to get to you one per second? So if I throw one bag every second, you receive them one every second. Okay. What happens if I start walking towards you and throwing them? I'm still going to throw one per second, but it is not faster. Be careful in your wording. Sorry to be Mr. Anal. No, but I'm still throwing at the same speed. What does appear greater though, Stephanie? You get them more often or less often? You get them more often. So actually it isn't the speed that goes up, it's the frequency. So I may throw them one per second, but because I'm a little bit closer each time I throw it, and has less distance to travel, it gets there a little bit sooner. So is your perceived frequency higher or lower, even though I'm throwing at the same speed? You perceive a higher frequency. Okay, what if I'm backpedaling? What if I'm moving away from you and throwing them? Even though I still have a sender frequency of 1, do you perceive a higher or lower frequency if I'm moving away from you? Lower, perfect. Now the weird question, if I'm moving almost as fast as I'm throwing them, does that mean I'm going to get closer at a much greater rate? I don't know if that makes sense, but let's say I'm throwing them at 20 meters per second and running at 10. That means I'm making a really large amount of distance up every time I throw it. So it might seem like a big deal to you. But if I'm throwing them at 100 meters per second, but I'm only walking at 1 meter per second, the difference between 1 meter per second and 100 meters per second is so minimal that you'll barely notice it. Does that make sense? Yeah, you won't be able to tell, or you'll barely be able to tell. Okay, so now let me go to why we usually use it for sound and we don't worry about it so much for light. What is the speed of sound in air? It's around this. Is the speed of light bigger or smaller than this number? Speed of light, if I remember right, is around, does that sound about right? Or actually, it's around 3 times 10 to the 8th. So would you agree this number is a tiny bit bigger than this number? Just a little bit. So on our planet, if we're moving at 10, 20 meters per second, 10 to 20 compared to this is what? 3 to 6%? See, a 3 to 6% difference in frequency, can you hear it? Definitely. This one, let's see, I have 10 more O's, so 10 to the 6th. So instead of being a 3%, it's a 0.0000003% difference. Can you see visually a Doppler effect in our planet, in the atmosphere within our world? We usually don't talk about it because we don't notice it. So where do you see things like a red shift or a blue shift? Nothing in our world will move fast enough to see a red shift or blue shift with our eyes. Perfect. Somebody said planets, somebody said stars. Yeah, so now to define what the Doppler effect is. Is the Doppler effect a real change in frequency or a perceived change in frequency caused by motion of either sender, receiver, or both? Ooh, that's a weird sentence. It's a perceived change in frequency because the sender and receiver are moving at different rates, including not moving for one of them. And then redshift and blue shift is what we call it when it's dealing with stars. So let's say long ago, the star gave off some light. And let's say this light normally had a wavelength of 517 nanometers when it left. But here on Earth, our blue planet, we detect that incoming wave at 516.4 nanometers. Am I perceiving it at a higher or lower frequency? careful on this one. So I screwed with you and gave you wavelengths. So are nanometers a wavelength or a frequency? I messed with you. I gave you a wavelength. So if it's a shorter wavelength, it's at a higher frequency. So lower this, higher this, because it's traveling at a certain speed. So it arrives at a higher frequency. That must mean one of two things. The star is moving towards us, or we're moving towards the star. So when you are moving towards one another, as you get closer, your frequency, just like when I was moving towards you, you got a perceived higher frequency. So isn't that true? Does the Earth orbit in an elliptic fashion around the sun? And therefore, are there certain times of year we're moving closer to the sun? Certain times of year we're actually moving away from the sun? We also have some spinning going on, but this is just straight out motion. When moving towards something, frequency goes up. So it's said to shift to the blue side of the spectrum. It ends up being a little bit closer to 400. So it went down a wavelength, went closer to 400, closer to blue. This is a blue shifted wave. So we get a perceived change in the frequency and wavelength caused by some sort of motion. Okay, that's sound or light. They have thrown both on the MCAT. You must understand what blue shifting is, moving towards the blue end of the spectrum, and red shifting, moving to the red end. And then you should be able to explain, like, let's say, I know the other day I was out in front of my house, the neighbors were driving by, and I'm jumping up and down, hi neighbors. And neighbors all seem to be, like, in this area, all sort of know each other, and they know, like, everybody's personalities and things. So I knew them well, and I'm all happy to see them. And as they drove by, I think what they said was, asshole, or whatever. Why did it sound that way? Why was it asshole as they drove by? What happened? Did they change their voice? Or what happened in that? So as they drove by, the frequency kind of went, eh. How many have actually heard that? Yeah, so, okay, to field all the questions that all came in real quick, the blue shift, red shift, yeah, if we're moving towards the sun, all the colors we see will be shifted slightly towards blue. So if we know that hydrogen gas gives off a 589, we might see it at 588. If we know that helium gives off a 612, we might see it at 611. If we're moving away from the sun, so if we look at the elliptic orbit, here's the sun, and we traverse it in this sort of fashion. So if we're moving this way, are there certain times of year we're moving away from the sun? Certain times of year we're moving towards the sun, moving away, moving towards? So we go from seeing exactly what we should see to now seeing red shifted, back to blue shifted, back to red shifted, to blue shifted. So that's light, because we're moving fast enough to see that. On our planet, we pretty much only hear Doppler shift. So if something's coming towards you and then away, it's like, it goes from really high pitch, because it's coming towards you, to a lower pitch. Okay, so just want to emphasize, when it's just straight physics on waves, they like the concept of red shifting, blue shifting, high frequency, low frequency shifting for sound, Doppler shift. Yep, lower pitch means lower frequency. I cannot apologize enough for why physicists have to throw in additional words, but yeah, pitch and frequency, I should be using them interchangeably so that depending on what a test writer gives you, but yeah, pitch and frequency are synonymous. So if something's moving towards you, it sounds higher pitch. If something's moving away from you, it sounds like a lower pitch. Okay. And does anybody have any idea why the hell they keep on adding unnecessary extra words? Nope, brightness has to do with intensity. So like a sound getting louder or quieter is like a light getting brighter or dimmer. That's an amplitude. Whereas a frequency change is an actual change in color or an actual change in the pitch. High to low, blue to red. So hopefully it seems okay. So I think we're onto something. So one thing is Doppler shift. It can apply to any wave, have to know it in general. And then number two, when I change medium, can a wave change in some way? How? So when you go from one medium to another, really important to note, does the frequency change or is the frequency set from the very get-go? The wavelength can change, perfect, and the speed can change, exactly. So if I change medium, the speed and wavelength can change, but frequency is set. And so here's a really good way to remember that. When I look at light, do you agree light has a certain amount of energy, h nu, hf? Sorry, just gotta so apologize. I'm being rude and on the phone at just a moment, just texting. And it's like one of those emergency interrupts. Not a critical one, but spouse related. Okay, so just I'm catching up on chat box. I so apologize. So just confirm and understand this correctly. Things move further away. Wavelength appears to increase. Exactly, it stretches out and frequency goes down. When it is moving towards you, it's the exact opposite, exactly. And when things move away, longer wavelength, they're called redshifted. So if, in this case, we're moving away from the sun, getting further away, we'll get a redshifted. Frequencies will appear to be lower, wavelengths will appear to be longer. When we make the turn, we come back, we start going the other way. We start coming towards, so we go from a red-shifted scenario to a blue-shifted scenario. And think about it this way. Have you ever heard a helicopter overhead? I mean, I don't know where any of you live, but where I live, there's with some high propensity, we tend to hear helicopters overhead circling around. Can you tell when you were the center of that circle? So if you're the center of a helicopter that's circling around, will it sound consistent? Will it always be the same distance away? So no change in frequency, no change in intensity. But if you were off-centered, then do you hear a Doppler shift and a change in loudness? Yep. So you can definitely hear this sort of thing. And then changing medium, again, when you change medium, frequency stays consistent. So what I wanted to point out is the energy equation, and this is, we'll focus more on this in E&M, but how many have definitely seen E equals HF? Sorry, that looks so poor. So what this basically says is H is a constant. So if I have a ball and let's say the ball is red in color, if I drop it into the pool, so I drop the ball underwater, when it goes into the water, does the speed of the light coming off of it change? Is it going to move slower now that it's in water? Sure, speed of light goes down in water. The wavelength has to change as well, but is it still a red ball? When I drop a ball underwater, does it change color or does it stay red? So what happens when you drop a ball underwater? Does it stays red? Same color, doesn't change. Because it's still red, it's the same energy, which means its H, the constant stayed the same, and the frequency stayed the same. Isn't that an interesting thing? So we always use wavelength in a vacuum to describe a color, but no, frequency is technically color, frequency is technically sound, but out of sheer laziness, in OChem especially, do we always talk about a lambda max associated with color? We have a whole friggin' color wheel we use. But the trick on that, the color wheel only applies in a vacuum or loosely in a low density gas like the atmosphere we live in. So we can use it, but once it changes medium, the color wheel doesn't apply anymore. So that all the memorization you did, 400 nanometers, 700 nanometers, do you ever remember professors, if they were really, I don't know, anal about it, always saying in a vacuum? So did they ever bring up in a vacuum as a caveat? Speed of light, in a vacuum. Wavelength, in a vacuum. They do that because it's going at its maximum possible speed under those conditions. But once it changes medium, it will change its speed, it'll change its wavelength, but the frequency stays consistent. So actually what you see when you see light, you actually see energy. You see the energy needed to excite up your cone, whichever one it is. And it does so by breaking a bond. Bond energies are precise. So thank goodness the frequency and H don't change, so the energy of the photon doesn't change. So whether it came from water, so whether you're looking underwater at a red ball, in the air at a red ball, in a tank of oil at the red ball, it's still going to look red because it's still going to have the right frequency in H to generate the energy needed to stimulate the red cone. Okay, so lo and behold, this sound lecture just turned into a light lecture. It was bound to happen. Okay, so moving on, a couple other things about sound. What I really want to hang on to is this notion here. These numbers I think are useful to know. And this equation is an absolute must, absolutely positively must. And then what is this equation? The one I drew up here? I can't remember what that is. So somebody's asked and I don't know. So anybody want to chime in exactly what the energy, H and F represent? Energy of a photon, or energy specifically of a wave of some sort, but we use this for light. H is Planck's constant, perfect, 6.6 times 10 to the minus 34. Not you should memorize it, but just wanted to impress you that it's one of those useless things. I've done so many questions, it's in there. Frequency times Planck's constant tells me the energy of a photon. Is this a pretty fundamental equation for light when you took physics? This one is for the energy of a photon. This is just generally for a wave. Not a lot of equations to know, but those should definitely be on your hit list. Okay, onward we migrate. Frequency is set by the source. That's the thing really want to emphasize. What it sends out, that's what it's going to be. Even when it changes medium, the frequency stays the same. Red light, if you start it in water, oil, air, doesn't matter. It's red frequency, it's going to stay red frequency. The loudness, how many have heard of the decibel scale? Like, oh, that was 107 decibels. I don't know what that number actually means because I don't speak the scale, but okay, so the decibel level represents how loud it is. What is I/O? And depending on how you answer it, I'll share the funniest answer I've ever gotten in my life. So it's a threshold intensity where we barely can hear. The best answer I ever got over all the years of teaching was, it's what they say on McDonald's farm right after EIE. I had to think about it for a second, EIEIO, and I thought that was genius. That to me was like those memorable things that this genius student. Yeah, I got a bit. It was pretty damn funny. And unfortunately, every time I see this now, I always think of that. Isn't that what they say at the end of their things on Old McDonald's farm? But anyway, intensity level threshold. Reality is we cannot hear at this unless we have perfect hearing. So we actually kick in at about 10, 15 decibels, depending on our ears. I know I ruined everything for you, but everything begins at Old McDonald's farm, so that's your threshold of hearing. Notice it depends on distance squared, meaning it spreads out. As waves travel, they spread out, so intensity goes down. So when you do the math, let's say you're 1 meter away from a speaker and it's 60 decibels. What will happen if you move to around 9 meters away? Or I'm sorry, not 9. I just totally gave away what I wanted. If you go from 1 meter away to 3 meters away, will it get quieter or louder? If you move further away from a speaker, hopefully you've experienced this in life, it gets quieter, okay? So let's figure out how much quieter. So if it's 60 decibels at 1 meter, let's figure out what it's going to be at 3 meters. So using this equation, the difference in decibel level, beta 2 minus beta 1, or the difference in decibel level is going to be 10 log. When you subtract or divide numbers, you're going to subtract logs. I'll worry about that in a second. But intensity at 3 meters compared to intensity at 1 meter, when I go 3 meters away, does it change by a factor of 3 or a factor of 9? Change by a factor of 9. So here it's 1/9 as loud. So 1/9 I1 over I1. So I just want to get that ratio. So 3 times far away, 3 squared is 9, 1 squared is 1. So ratio of 1 to 9, so 1/9 to 1. Going to cancel out the I1s, cancel out the 1 on bottom, log of 1/9. How many are okay with me saying that log of 1/9 is roughly log of 1/10? They're so close. 1/9 and 1/10 are so close numerically. I'm going to just use them interchangeably. Plugging in. So take this number here, you tripled your distance, and it's squared. So what do I get when I square 3? Thanks, Brooke. Perfect. So it depends on, because it depends on distance squared. Exactly. So it's really 1 over r squared, as Melody stated. That's actually the correct statement. Because we're going further away, it's dropping. So the intensity dissipates or drops with d squared, but that means we multiply it by 1 over d squared. Perfect. Okay, so with that in mind, log of 1/10 is -1. So plugging in 10 times -1, -10, it drops by this. So every time you triple your distance, you drop the decibel level by about 10 decibel levels. You'll probably experience this with a jet. So if you've ever been anywhere near an airport, let's say jet's a few miles away, makes whatever sound it's going to make. No sound doesn't get louder, but also when it gets close, it gets super loud when it flies overhead. How would definitely agree? Miles away, a few miles away, 100 feet away, not bad, but once it gets close, does it shoot up pretty drastically? Is this your 1 over d squared, as somebody just said? So here's a thought. Are earbuds good or bad for you? So which would be better, having earphones that you put over your ear or earbuds which you push into your ear? So why are headphones better for those who said headphones? You're not getting them extremely close. How many have ever noticed that if you push your earbuds in, it gets noticeably louder? So if you want to pay off your med student loans faster or faster than the average doctor, go become an ears, nose, throat, ENT doctor, because are there going to be a whole bunch of earbud deafness cases coming up in the next 20 years, 10, 20 years? Yep. Oh, somebody brought up a good point. How many have ever put their earbuds in the wrong way? Oh, it's personal, Elton. Why am I attacking you? Because I'm evil and mean and it's personal. Come on, you should know that by now. But no, has anybody ever put their earbud in the wrong way? I know, I'm actually wearing earbuds right now as I'm going through this. Yep. I'm going to recommend, if you want to pay off your med student loans, invent the following. So this is supposed to represent an ear. I don't know if this is a very good drawing. In fact, I know it's a terrible drawing. And if you have a green ear, you might want to go get that looked at. But have you ever thought about putting a little speaker here? And instead of calling it an ear ring, call it a hear ring. People would buy this. If you put doctor there, and the reason I say that, are there already physicians that are in the ear, like the headphone industry? I mean, there's a very famous ENT, ears, nose, throat doctor. I believe, I don't know how to pronounce his last name, but I think he's an ENT, ears, nose, throat. But he puts out a lot of sound equipment. You can replace him. There's an opening there. Dr. At any rate, I definitely think all of you should consider that as a field. Last but not least, sound ranges from 20 hertz to 20,000 hertz. How many never had to learn that when you were in school? How many not even once were taught that range? I wasn't. Never showed up once. Yeah. Now, I had to learn 400 to 700 for light. I had to learn it in GChem, OChem, and bio. They beat that one into me, and physics. Yep, my goal is, I'm getting a kickback from the ENT industry. They need more. So yeah, that's actually how I make my living. So that is so true. So today's lecture is sponsored by the ENT Society. But When you see the word ultrasound, how many think A, a sound you can't hear, or B, imaging? In fact, finding a baby. Okay, so I want to figure out how it's going to work. So I'm going to jump to the next slide. And yeah, I don't know, but and this is a question I have from what you've heard. How many have heard that there's certain hospitals that will now, like Kaiser in particular, has med school now, and it's like hop, skip, and a few blocks away from where you live. Okay, quite a few miles, but still out here. Are those doing well and going to catch on, or do you think those are going to fizzle out? Basically, they'll pay for your medical school, but you owe them a portion of your career. Because somebody was just mentioning, like, you'll be an ENT if they'll pay for it. Wait a minute, is it known that NYU now has tuitionless med school, which ends up, it's not quite as tuitionless as they say. There's still a lot of fees and insurance you pay, but it's nothing compared to the other ones. How many heard like certain Texas schools for Texas residents, it's free? Yep. I want to quote somebody there. So somebody apparently used to work for KP, Kaiser Permanente, and saying nothing is free. Kaiser isn't only starting one, Kaiser did start one. I mean, I think it's in Pasadena out here. Now, I don't know what I mean, there aren't enough people who like given feedback for me to have any clue whether what's going on there. Yeah, they haven't graduated anybody. So, or is that true? Gosh, I've lost track of time. COVID has screwed up my sense of time so severely, but I don't think any of them are practicing physicians yet. And certainly, yeah. So, I mean, it's still relatively new. Okay, that's what I was thinking. And you know what's so sad? I knew when it started, I didn't know what this year is. I'm so embarrassed. But yeah, so yeah, it's a profit med school. But the reality is it's going to change the dynamics. If it works, other med schools will start tying off with hospitals. You can guarantee it. If it doesn't work, it doesn't. I'm so curious how this will work out. Well, how many years are you planning on staying in med school? I hate to be the one to really catch you off guard by this, but I think after 4 years, they kind of make you leave. Oh, okay. The first 4 classes. Ah. I'm so sorry. I didn't mean to be rude, but it just was right there, low-lying fruit. Yeah, if you can make med school last about 20 years, you never really have to pay off the loans. Good call. Smart thinking. Okay, so back to this. Ultrasound imaging. So if the patient comes in, let's say the tum-tum stores said offspring. And oh, by the way, stick figure, square-headed babies are all we learn about in this class. Can you find that baby? So if I put my ultrasound device here, would that give me a good experiment? Would that work very well? Why not? What have I messed up? Oh, okay. So the question is, why it's square-headed? It's square-headed because I'm a terrible artist, and just a blockhead baby is all I can draw. So this has nothing to do with reality. This is my inability. Ah, perfect. Somebody just nailed it. A few of you nailed it. At every interface, you have to worry about the density of the medium. If this is a solid or liquid-like solid, the tum-tum, and this is air, is that a large or small difference in density of the medium? Large difference, which means mostly reflection or mostly refraction. Most will reflect off it, or most will pass through into the new medium. A lot of reflection, meaning you might lose 90% of your initial wave. Not going to work out well. So what do they do to alleviate that problem? Oh, the relationship is basically, and it's going to pop in my homework, so I'll leave the equation for then. But it's basically the bigger the difference in density. So it's the difference in densities. As that increases, the amount of reflected wave goes up. So if the two media are comparable in density, you get almost complete transmission, very little reflection. But if you have air and solid, you get substantial change. That's again why we soundproof by having solid, gas, solid, gas, solid, gas. So a lot of that wave reflects at the interface. Okay, so you're telling me this technique isn't going to work too well now. So what if I blob a whole bunch of gel on the patient and then put it in like that? Now is that going to be a little bit better? So how many have worked in neonatal? How many have actually, or prenatal, I should say? How many have seen an ultrasound in action? Or let's say you're just, I guess, imaging some sort of other body part, let's say a knee or something. So how many will confirm the fact that, yep, they put gel? And how many will confirm that they don't even bother warming the gel? They just put ice cold gel on the patient? No. But they put that on there and then they stuff it on there so that you get one less reflection. So it goes in. What are they doing this for? Why are they looking for this? Okay, so one person said you run it under warm water. And I'm so sorry to make this almost, it's going to come across as sexist, but for the person who said you run it under warm water, is that office mostly women who are sensitive and understand, because at least one or two of them were on the other end of receiving when it wasn't considerate? Perfect. Yep. And I just, okay, yep. Sorry, I'm trying to dance this as best I can, but it just, women doctors in my experience have always been far more sensitive and considerate of their patients. So sorry about the blatantly sexist comment, but it's just, I mean, it's just the track record of everything we've dealt with. Not 100%. There's going to be an exception here and there, but I just, when you said that, I pictured where my wife went. And it was awesome. They were really good about things. Okay. That said, when this wave hits and reflects back, what is it actually detecting? So when you do ultrasound, what are you looking for? Yeah, see, I'm not going to go down that path. I just think the perfect system would be like the family. Set it up with I don't know, whatever. It's echolocating. Is the skull a different density than the liquid and the brain and the tissue? Calcium deposits, bone, exactly. Can you echolocate the solids? And depending on how much time it takes to reflect, can you image accordingly? So do they ever use, let's say, an ultrasound to figure out if somebody has a tear in a ligament? I mean, is that also one of the procedures? I mean, ultrasound is useful in many ways. MRI is probably what they're going to ultimately use, but do they ever do initial imaging for a tear? Do they do ultrasound for anything? Yep, because if there's a tear, is there the slight possibility or the good possibility there might be liquid filling in that tear region? So if you have a tear in a ligament, so let's say the ligament is solid, but you got a slight tear that's filled with liquid. If you send it the right way, can you get an echo here and here that you normally wouldn't get in a solid ligament? Okay, I'd actually want to tap into this. So who? Perfect. So Brooke, if I'm remembering right, and sorry to, I'm saying something I think you already said to the crowd. You were a college athlete that destroyed your body, right? Or you did a sport that beat the crap out of you over time? Yep. So you've been on the wrong end of doctor visits more than the average person. So, and did they actually do an ultrasound to find a tear in a ligament? Perfect. Okay, so if, and the question is, oh, that's actually a really good doctor. My question to you, did they only send it in one direction, or did they change the angle multiple times to get it imaged? Lots of angles. Why? Why? They want them to see the interface from all different sides. Good three-dimensional image. Perfect. When they do ultrasound trying to find an offspring in somebody's tum-tum, do they do it from one position or do they move it around? Move it around. Anytime you try to image anything, you get multiple angles and you get your echolocation. It is just amazing how this thing works. But you put gel on there to reduce the number of interfaces so you get a more intense reflection. Okay, and so Brooke, sorry to bring this up, but did they gel your I don't know why I'm assuming knee, but did they gel the heck out of it? Ankle? Okay, and did they gel you like crazy? Oh my gosh. Unique. Do you mind sharing that at all? I mean, obviously you put it in public chat. So holy crap. So they found a clot, which would make sense. It's a different medium. Holy crap. I have no idea how common that is, but a childhood friend of mine, hadn't seen him for years, ran into him again. He had a big scar down his entire jugular, and that was exactly what the thing was. And it's just so random because that's exactly what he said. It's just completely rare. And they only found out because he failed a physical for playing on a sports team. And it's like they caught it literally at just a random nick of time thing. Man. So glad it worked out. Sorry as hell you had to go through that. Okay, what happens to an uneven surface? So let's just say, I don't know, maybe I lied to you about the square-headed baby. If you have a surface that is not smooth, you get a cleaner reflection, or is it now a scatter plot? Scatter plot. Weird and true story. If you look back in the late 80s at like completely useless products, there used to be a product you'd put on your license plate. So here's your license plate. You basically sprayed it on, and it was very much like rubber cement. And what it did is the radar gun that police use have to come in, hit your license plate, and reflect back. Because the one thing every car must have is a license plate. So if they can use if the ticket holds up in court with a laser or a radar gun or however they detect it, it has to be on a surface they know. So people would put this on here. Because how many have ever seen those plastic covers on license plates that are sort of murky or cloudy? Those came into being to try to not get recognized. And quickly people realized that the police were shooting anywhere and lying and said they hit the license plate. But there was a product that literally sprayed on your license plate so that it would scatter the reflection and they couldn't get a signal back. So they couldn't figure out how fast you were going. Amazing or amazing scam. But yep, I'm from a generation where we bought pet rocks and crafty spray on your license plate to prevent tickets. So yeah, this is the kind of thing. That's how you pay off med school. Yeah, yeah, you're off by a generation if you went to suckers. We were pretty bad. Where should detectors be placed? So I want to bring up something that's kind of a little outdated at this point. But hypothetically, let's say there was some cave. It was in some mountain. Let's say this cave had areas where soccer players could go in, little kids, and get stranded, and you had to find them. Could you put these devices into the mountain and send signals down to try to figure out what was going on in the cave? How many remember this, that Thailand rescue? Yeah, I mean, I was just obsessed like nobody's business. I used to scuba dive. I took a rescue class and I freaked out in a cave. That's when my career ended. The people who do this are the bravest, craziest people on the planet. And so thank God they're there, because this was a truly a miracle. Oh yeah, see, splunkers always died. That, I mean, but these were kids that got flooded in. What they didn't tell you, and a lot of the things they did, is they put infrasound in here. And so the key thing is you want to use infrasound because it's this long distance from the mountain down to the cave. Is that a pretty good distance? So what were they looking for when they did this? Were they looking for the actual kids, or were they looking for air pockets? Yeah, no, somebody brings up that one every time and I just freak out, don't want to do it. So splunking is what it's called, where you go in there and you go through these crazy caves in the dark. And yeah, you go over cliffs and you don't realize they're there. There's also a case where somebody got stuck upside down for so long, they hemorrhaged. So you're looking for air pockets where they could potentially be, and then the scout divers went in. The fact they found those kids is a miracle. The fact they got them out is beyond a miracle. But it's that's how they ended up having to do it. So the point trying to make with this, short distance, we use ultrasound. Long distance, we use infrasound. Which is a longer wavelength, ultrasound or infrasound? Infra is much longer. We use infrasound for geological surveillance or surveying. We use ultrasound in medicine because the body is a short distance, which leads to the last thing I want to toss up here. Let me get rid of my terrible picture. This showed up on the MCAT a couple times. They gave students this information. This is not something to memorize, but they gave this in here. But what it basically means, if it's a short distance, use a short wavelength. If it's a long distance, use a long wavelength. Yes. Oh, I'm so sorry to get excited. I'm answering a private question, which I probably should share with everybody. The question was, does echolocation just mean reflection? Yep. You send a wave out, you see what it reflects. High intensity, probably a solid. Medium intensity, probably a liquid. No intensity, penetrated through. Same density you're dealing with. Yeah, so the what classifies as long, how far is it from the surface of the tum-tum to the, I don't know, the skull of a baby within the womb? Not long? Perfect. Somebody said maybe 20 centimeters. Seems reasonable. By 20 centimeters by 200, and that's the wavelength you should be using, about a millimeter. Whereas for imaging that, let's say it was a kilometer from the top of the mountain to where the cave was, then you would end up using like a 5-meter wavelength. Oh, it just, so the question is, what exactly does a receiver receive? Let's figure out, how do your ears work? Because that is actually kind of the same answer. So how does sound impact your ear? What actually happens? So tell me how sound propagates. Perfect. So some frequency hits your eardrum, but let's be more specific. So is your ear a funnel? Does your ear catch sound and funnel it in? Perfect. Okay. So it's going to funnel it in. And inside your ear is an air-filled canal or a liquid-filled canal? Trick question. Air for a while, but does it pass through the drum into a liquid-filled region? So are the cilia, the little fibers that actually get affected, are those actually in a liquid rather than air? Ooh, endolymph? I have no idea where it is, but I'm going to believe you because it sounds bio enough. but it's gonna, is it endolymph fluid? Is that what they call it, you're saying? And this I don't know. I'm quoting somebody in chat, so I'll go with that. But as it passes through in your cochlear canal, and I'm totally making up words now. Forgive me for this picture, but I'm gonna kind of cheat and in a way I'm gonna be proud of in a second here. And this thing is not perfectly straight, it wraps around. But how many learned that with in your ear, there are these little fibers? Shoot. Long one, medium one, short ones. How many have learned that you have these little fibers, there's little cilia? As a sound goes in, if the sound is the right wavelength, can it vibrate the right fiber? No, I know what your question was, and that's what I'm saying. So your question, how does ultrasound detect a baby? How does it detect anything? And I'm saying it's very similar to how the ear works. So can the ear hear the right frequency? It can have specific fibers. So now let's take this same device, put it into a fluid. I'm going to send out that pulse. It's going to hit something and come back. When it comes back, my detector is literally this, a whole bunch of fibers in a fluid. Will it trigger what frequency we just sent in? So in other words, if I send in a very high pitch, a very short wavelength, then it's going to trigger these fibers. So basically, the more reflected waves, the more the fibers get triggered. The less reflected waves, the less they get triggered. So it's basically the number of fibers that get triggered is how it works. So the reflected ray is going to come back and it's going to interact with something literally designed like your ear, where you have these cilia that pick up the vibrations. So if that makes sense. Yep, exactly. The more reflected waves, you know, two things are true. Number one, it reflected off of something of higher density because you get more reflection. And then from that, depending on how soon the wave comes back, can you figure out how far away that object is. So it's going to pop up. I'm going to switch slides because I think the next one might be more helpful. Here's the right one. So I apologize. Clicking in 3, 2, 1. Yeah, echolocation. So let me do this and then we'll work backwards. So you have done echolocation in your life maybe and didn't even realize you were doing it. Oh, if you increase the intensity of sound you're sending out or ultrasound, you're going to get higher intensity back. But all I care about is like what it hits. So let me power through this, and then in 2 slides it'll hopefully work out. But I want to start with a simple analogy. How many of you when you were kids played a game called Marco Polo? Okay, so a few yeses. So I think this game works because you yell Marco with your eyes closed, supposedly, but most of us cheat. Everybody else says polo, and you have to sound locate them. Well, let's say you're a physics kid. Do physicists have very many friends? None. They have a slightly different game. Instead of playing Marco Polo, they play a slightly different game known as Marco, the game of echolocation. So can they go in the pool and yell Marco, and when it hits a wall, can they see how long it takes to come back? And from that, can they figure out how far away the wall is? Or some object floating in the pool or something. So echolocation, you send it out, it comes back. So the longer it takes for it to come back, what do you know? Can you figure out where it is from how long it takes to come back? The farther the wall is away. And can you tell whether it's a spongy wall or a hard wall based on how intense it is? Sure, because the harder the wall, the more intense the reflection. Softer the wall, the less intense the reflection. So I can figure out how big it is, I can figure out its dimensions, how far away it is, and I can actually get close to what the material is. So if we're seeing it, can I just listen to the echoes coming back and deduce how far away it is and what it is? Okay, stationary object, ultrasound imaging of a baby. But how many learned bats and dolphins also use it to catch prey? Ah, beautiful. How many understand what Marissa just said? The acoustics of a recording studio, and when you say carpet, carpet on the floor, carpet on the walls, carpet on the ceiling, carpet friggin' everywhere of different types of carpet. So have you ever heard of something, it was popular in the 70s called acoustic ceilings? You ever seen that spongy foam they put on this on the ceiling? Like every building built in the 70s had that crap sent or sprayed onto the roof. It was designed to scatter sound, to absorb and scatter sound, so you didn't get an echo chamber. So yeah, you soften the surfaces to scatter the sound, absorb the sound, reflect the sound in random ways. So hopefully all the reflections start killing the intensity of it. But dolphins, let's say we have our dolphin here, our random fish here. Can it figure out the following? So let's say sends out this wave, sends it out, but bam, just hit it, gets the echo coming back. Tell me about the echo. Oh, popcorn ceilings. Yeah. Yeah. The formal name, I guess, is acoustic ceilings, but yeah, they're popcorn ceilings. That, and how many know what the heck I'm talking about? Those little spongy little, I don't even know how to describe it, but anybody ever push your thumb to crush it when you were a kid? Okay, thank God I wasn't the only one. And yeah, but that was basically that. The genius of that maneuver was, let's put some toxic waste on our ceiling to cut down sound. Oh, I never picked at it. I just smushed it. Oh, I'm so happy to hear that all of you are freaky weird people too. This is awesome. Okay, so what would the dolphin be detecting? That wave is going to tell a few things. Tell me about the reflected wave. Would it tell me how far away that fish was when the wave hit? So with the time there and back from that, be able to tell me where it is? Sure. Would the frequency of the reflected wave be the same as what it sent out? Or because the fish was moving, would it actually be a change in frequency? So would it come back higher or lower, the frequency? Lower frequency, because was the fish moving away or towards? Moving away. So can it tell where it was when the wave hit, whether it's moving towards or away, and to some extent, how big it is? A loud echo comes back, run away. Tiny echo comes back, go catch it and eat it. So I want to kind of combine all this, but does this make sense that what you're doing? You're sending a wave out, hit something here and reflect it back, there and back, trick they like to say to you. So let's say it gets the echo in 0.1 seconds. How far away was that green object when the wave hit it? So I'm going to tell you it was either 34 meters, 17 meters, or 50 meters, 75 meters away. How far away was it? Trick question. There are two things going on here. The echo is the distance away or the distance there and back, both. It's there and back. So total distance equals 0.1 second, the time, times however far it is meters per second. I forget. What is the speed of sound? This was a dolphin and a fish. 1,500, exactly. That's a total distance. So the total distance equals 150 meters. So 75 there, 75 back. Is this a classic trick question, the there and back trick? Yes. And is it a classic trick question to confuse air and water? I threw a double trick question at you. Do not feel beat up, offended, hurt, or any of those emotions, because I set you up for two of the very common things they do. There and back to mess with people, air compared to water. Okay. Applying it to system. This is the one I was trying to build at. So once upon a time, the land far away called the previous MCAT, they were talking about trying to figure out sedimentary layers. Yeah, so somebody in private chat just found the loophole in this whole thing. So if you hit a different density object, the intensity is different. And that tells you one thing, but also does intensity tell you how far? Because does it dissipate with distance? So time tells you distance if you know the speed, and you get intensity from the hardness. So you have to take both into account. Okay, so I'm going to do this experiment. I want to point something out. Apparently the Earth is flat. I've been told by somebody recently about this. So that whole sun being a sphere thing didn't really influence them in believing that we weren't flat. But so obviously the Earth is flat. So therefore, are all the layers flat? Sure. So I'm going to send this wave in. The wave's going to come in. It's going to hit the first surface and echo back. So first echo 1.3 seconds and an intensity of 6.42 of whatever unit. We get a second echo. So I want to analyze a few things that are going on here. To go there and back took 1.31 seconds, but to go there and back took 2.44 seconds. So how long would it take to go from here to here? I guess you can see blue. How long does that take? Perfect. Difference between the two, perfect. So it's going to take 1.13 seconds to do that. And then if I want to figure out how long that distance is, could I do speed of sound, that medium, times 1.13 or times 0.565? So if I want to actually measure the distance from here to here, does that make sense that I'd have to take the time from here to here times the speed of sound in that medium, but half of it, because there and back, so perfect. So can I figure out how deep this layer is and how deep this layer is from this experiment? Definitely. Does this make sense, how to image this way? So this goes back to the baby, the outside of the skull, inside of the skull. And I don't want to give things away because there's a couple homework questions that are specifically designed to analyze ultrasound data, really simplified, like MCAT level, not med school level. But I don't know, I find it pretty interesting. Okay, moving onward and upward. I want to toss 3 questions at you, give you about 30 seconds on each. So starting in 3, 2, 1. Oh, so question just popped up, sorry. Oh, no, no, intensity has to be a reading. So that had to be a given in that question. So the intensity was just a number there. And the key thing was it was about 4 times the other one. And it had a lot to do with the distance. They had roughly equal reflections. That's what you conclude from that. But we didn't do anything with intensity. We did everything with time. So intensity was extraneous. Okay, starting in 3, 2, 1, and you're off. So sorry to give that much time. But back, so what do I know? Tell me about speed of sound. So first and foremost, longitudinal or transverse wave, hopefully that's a freebie. Longitudinal, that helps. And then the question is, when you go to a thicker medium, what does that mean about the speed? Speed should go up, perfect. But what does that mean about wavelength? So I've got to go to the equation. What stays the same when you change medium? Frequency stayed the same, so no change to frequency. So if the speed went up, according to the relationship, what has happened to the wavelength? Has to go, oh no, no, it has to go up. So if it's up on one side to keep the equality, if the left side gets larger, the right side has to balance it out by. So hopefully it seems okay. So is this just a small twist in what you normally know? Yeah, so basically, if the speed is going faster, a couple ways I can do it. I can go up and down twice, or up and down once, excuse me, up and down. But can I do this? So which is going to be faster? If it takes the same amount of time for this wave to go up and down as it takes for this one to go up and down, but this one covers a longer distance. If you have a longer wavelength in the same amount of time, you're going to be going faster. So according to the equation, if F is constant, frequency doesn't change when you change medium, V goes up, wavelength has to go up to balance it out. How do you know the speed was faster? Oh, just one of those things we know about solids. Solid compared to a liquid, liquid compared to a gas when I deal with solid, or sound, excuse me. When atoms get closer together, molecules get closer together, particles are closer together, speed of sound goes up. It's memorization of one of two things. So speed of sound in water, 1500. Speed of sound in air, 340. Thicker medium, more compact medium, speed of sound goes up. So hate to say it, but just straight memorization at this point, but just the faster the particle can hit its neighbor and come back to original position, faster it restores, the faster the sound. Okay, next question. It's freezing up on me. I'm going to try clicking on this one. I just don't understand Bluetooth sometimes. Yeah, the answer is A. Okay, so what part isn't making sense? So there's two parts in that one. So I mean, sorry it's off screen. My Bluetooth finally caught up. But there's two things going on. Number one, does it make sense that the thicker the medium, the closer those particles are together, they're going to hit their neighbor and come back faster? Oh, okay. Yeah. So hopefully it seems okay. For this one, math related question. So I'm going to see what I remember math-wise. The equation, the change in decibel level when you go from one intensity to another, one position to another, whatever it is, 10, I don't know why they put the 10 there, but they do, log of one intensity over the other. If it's double the intensity, do you agree this is just a ratio of 2 over 1? So I don't know what log of 2 equals. This is totally up to you. So did any of you take the time to memorize the prime logs? Log 2, 3, 5, and 7. Take the 3 and move it here. Take the 5 and move it there. Take the 7, move it there. Put a dot in front. And then that one I just memorized is 8, 4. And this one is actually 4, 8 and 8, 4. You want to be precise, so 0.48, 0.84. But if you memorize that, then you know then 10 times 0.3 would be 3. You can get that straight away. If you know your math, perfect. If you don't, it's okay. I know log of 10 equals 1, log of 1 equals 0. So 10 times log of 10 would be 10, 10 times log of 1 would be 0. Would it make sense then that 10 times log of 2 is less than 10 but greater than 0? Only number here that's less than 10 but greater than 0 is A as in awesome. Okay, honest answer from everybody. When the screen just popped up with somebody's camera that just came on, anybody jump like those stupid things you're staring at and something pops up? Okay, so one other person just admitted to it, 2 other people. Yeah, it startled the crap out of me. Oh, no, it's totally fine. I'm assuming it wasn't on purpose, but it reminded me of those pop-up things that my kids would get me at or get me when I was a kid. Yeah. Okay. So this one hopefully seems okay. Again, log of 3 or log of 2 is 0.3. 10 times 0.3 is just 3. Oh no, I mean, I'm sorry, I should have let it go. It was no big deal, other than it popped up and just freaked me out a little bit. So I'm hopeful that we can all sort of laugh at our oddities and quirkiness. Probably give you about 30, 40 seconds. I do like somebody posted choice E. I do like that greatly. But for this one, this question is highly inspired, and I love it because they had a Cars moment. They took this was written by a Cars person, I'm sure, that accidentally went down the hallway, went in the wrong door to the physics test writing center and used their car as tricks. So a few things we can eliminate. How many got rid of certain choices because they know they're just wrong? So how many agree the frequency doesn't change with the medium? That's just out and out wrong. So A is wrong because it's false. What about B? The wavelength of sound is shorter when the wave is traveling towards the glass. They're trying to trick you with some Doppler stuff that doesn't apply. There's nothing Doppler going on here. Is this true? Does sound travel more slowly in air than it does in glass? Completely true. But is this also true that part of the sound wave is reflected when it strikes the glass? Uh-oh. Is one of these answers true and relevant? Is another one true and irrelevant? So they went with that. Just because something is true doesn't mean it's the right answer. So C is a completely true statement, but does that explain why the sound intensity would be affected? Not the density object, the bigger the difference in density between the two. So reflection is a result of the greater difference in density. So if you have two things that are both highly dense and you put them together, you're probably not going to get much reflection. But if you put something like a really dense material like glass and an air gap between it, that's what happens. No, the lower the density difference, the lower the reflection. So it's basically when you have a wall between you and a neighbor, does it filter out most of the sound? Yeah, nothing to do with refraction. This is purely a reflection phenomenon. Oh, okay. So what you're saying, yeah, no, I just realized, I just read, I screwed up reading reflection and refraction because we haven't even addressed refraction yet. So I'm going to stay strictly on the reflection phenomenon. But yeah, what you just said, if you have less reflection and more refraction, so your statement is true. I honestly just read reflection. So I screwed that one up. Okay. So for this one, is that true? Do you lose part of the sound when it hits the glass? Sure. Okay. The question was, why is this wrong? Frequency does not change when you change medium. So when it goes from air into the glass, frequency did not change. That's why that one's false. And the wavelength is the same whether it's traveling toward or away. So whether it's traveling towards or away doesn't matter. So if it's traveling in air is all that matters. So the medium is going to affect it, not the direction. So the wave going up is the same wavelength as the one going down, one going right, one going left. Those all the same. I don't know what to tell you. This is that whole idea. A ball that's red underwater will be red in air, red in oil, red in a solid. It stays the same frequency. No idea. I mean, this is just one of those things that if you're taking a hose and bouncing it up and down, when the water goes from in the hose down in the air, it's still going to go up and down at the same frequency. Just frequency is one of those things that just is an inherent property from the source. So if you fidget, that everything around you picks up that fidget is going to have the same frequency of fidgeting. It might not move as much, but it will fidget at the same frequency. Okay, this is true. Every time it gets reflected, you lose a little bit. This is true and irrelevant. This is true and going to cause it to be quieter. So a double paned window, if you live near an airport or a freeway or something, you'll have double paned windows because sound is being reflected at each of those interfaces, kind of like the way a jet is set up. Hopefully that seems okay. So D is your better true answer that explains it. C is a true statement but does not explain it. It's just, again, speed of sound in solid is faster than speed of sound in gas because the particles are already touching. You hit them, they'll come back sooner. Speed of sound depends on how fast a particle can restore its original position. So if I have gas particles, they have to come all the way over here and they come all the way back. If I have two solids, they move a tiny bit, move a tiny bit back. They're already there and be ready to hit again. So let me ask you a different question. If this doesn't make sense, that's fine. Then let me give you a scenario. Let's say you go to a sporting event. And have you ever had to, let's say somebody orders peanuts or something and the vendor passes it down the aisle, like the money gets passed one way and the object gets passed the other? Which is faster? If everybody's packed in, let's say there's 10 people in the row, can you go one to another, to another, to another, and pass the peanuts really quickly? But what if they're spread out? What if the 10, but they're not seated right next to each other? So one person here, one person here. So they can't just reach over. They have to get up, walk it over. That is walk it over, walk it over. Is that going to take more time or less time than if you could just pass it along to people? Which is faster? I mean, it's an analogy, but hopefully that makes sense. If you have to pass something down and get up and walk to do it, it's going to take you longer than if you can just hand it off to somebody right there. Solids, hand off the collision. One to another, goes very quickly. Gas has to move over, collide, move all the way back, get hit again, move over, collide. So hopefully that analogy helps. If it doesn't, memorize. Faster in a solid than a liquid, faster in a liquid than a gas. It's just what it is. Okay. So why wouldn't you talk to your friend through a window? Oh, why don't you? Because you lose some of the sound. I mean, do you agree if your windows are down, you don't hear the outside world as much as when they're up? You put a barrier, some's going to hit it and reflect out, some is going to pass through. I mean, why do you cover your ears? If something's really loud, why do you cover your ears? Why is that going to help? I mean, does it help? If the sound is really loud, does it help cover your ears? Okay, why? Why would putting your hands over your ears help you at all to not hear it as loudly? Doesn't slow the velocity of sound, it reflects the sound away. It is quieter because some of the sound is going to go from air and hit your hand. Some will pass through your hand into your ear, but most will hit your hand and reflect away and never make it into your ear. Soundproofing has nothing to do with speeding up or slowing down sound. It has to do with reflecting it and therefore redirecting it. So if there's a wall in a way, sound will not go through as much. Some will still go through, but most of it will reflect back. Cover your ears because you create a barrier so not all the sound can get into your ear. Some is going to reflect off your hand. It's just when a wave hits an interface, all the way back to the first statement, reflection, refraction, absorption can all occur at the interface. So if you want to have as little get through as possible, increase the amount absorbed or increase the amount reflected. So it's not particles, by the way. So just velocity and intensity are two different things. Whether it's a fast sound or a quiet sound, I don't care. When it hits that barrier, it's going to bounce off. So like anything, you open your window, more stuff can get through that hole than if you have the window closed and reflecting things away. It's just stuff gets in the way. A solid, if you're sending sound through air and a solid's there, it's going to hit the solid and reflect back. Not as much is going to get through. Independent of speed, not worried about speed at all. It's just if a barrier's in the way, it's going to stop it. Cover your ears. You don't hear as much because it reflects away. Okay, I'm going to field a couple more privates, but I really want to get going on this. It's just Yeah. So ultrasound, you send a wave in, it reflects back, you analyze the reflection. Intense reflection gets there fast. It must have hit something of different density, and it must have been close. Get it back fast, but it's low intensity, then it must hit something close, but of comparable density. So anyway, I kind of want to move on because there's, yeah, just time wise, it's time to march on. What is this wave? So this was something they had on test once upon a time in Land Far Away called maybe a few years ago. Oh, no worries. I mean, we can cycle back the end, but want to get through this? Not a tuning fork, because a tuning fork, when you hit a tuning fork, you get one sound, multiple sounds, I forget. So a tuning fork is a whole bunch of different frequencies or one specific frequency you're trying to match. Just one, okay? If you have no clue, an honest answer, how many have no clue what's going on in this one? When in doubt, sound it out. Is it getting louder or quieter at first? It's getting louder, but then all of a sudden, is it getting quieter? So would you agree, louder and quieter? Is the frequency the same the whole time, or is the frequency different before and after? It is different. So is it high or low pitch at first? High frequency because the wave is compressed, low frequency later on. So let me analyze this. Initially, amplitude is increasing, getting louder, and later on, amplitude's getting lower. It's a high frequency turning into a low frequency. So let's sound it out. So what did I just describe, or what did that sound just do? So Doppler. This is a Doppler wave. How many are like, damn, that's pretty tricky? Yep. And you know, as silly as it may be, in left field, I mean, that's exactly the best way to do it. Is getting louder than quieter, going from high frequency to low frequency. So what's happening in this front part here? Perfect, towards. I did something real subtle, but did I do it in blue? Because when you move towards, it's blue shifting. And then here, moving away, that's red shifting. So real subtle, but hopefully that makes for some accuracy on this. Hopefully it seems good. Okay. Which way is this ambulance moving? Backwards or forwards? Moving to the right? How do you know? So I got to the right and forward. How do you know? Compressed frequency, compressed waves. So high frequency, you're getting more waves. Here you get less. So compressed waves, shorter wavelength means higher frequency. So it must be moving in this direction. How many have seen this equation before? The Doppler shifted frequency equals the original frequency times V await plus minus V receiver over plus minus V sender. I never want to use that equation in my life if I can avoid it. And that's going to be one of my goals. I'm going to use it one time, come up with a shortcut, I hope. I do want you to know this much at least. Honest answer, not the politically correct answer, not the programming answer, but the honest answer. Is it better to give or receive? Sharing is caring. Look at this. Okay, we have honest people and we have people typing give. Who ends up on top? The person who receives everything. Ask the tax collector. I mean, just the way it is. The equation proves it right here. The receiver ends up on top, the giver ends up on bottom. The reason I say this is because they make so many subscripts. How many learned this? Oh, I know. I'm just joking about this. Please don't. I don't mean so cynical. In fact, I'll go off on a 30-second tangent on this. But the phrase "money can't buy you happiness" is a complete lie. Money can buy you all the happiness in the world if you know how to spend it on gifts for others and give things that people really want, need. If you want to make about happiness for yourself, maybe not. But if buying happiness means buying something that somebody really can use, a cold person, you buy them a jacket, a hungry person, food, you've bought happiness. So, I mean, it just is what it is. It's anyway, I'll leave that for what it is for this one, just being the cynical person, receive over give. How many learned the sender, receiver, source, detector, listener, speaker? How many learned subscripts like they were all over the map? So someone has to give the wave, somebody has to receive the wave. There are way too many subscripts. Totally agree with that. There are just so many of these damn things. So I'm going to reduce everything to receiver, the person who gets it, and the giver and receiver. Okay, with that in mind, I want to learn through questions. I'm actually going to do this by doing a question together. But I want to solve this one, come up with a game plan, and then solve the next one. So for this one, receiver is moving toward. Does toward make a difference? Is that one of the very first things you should be looking for, toward as opposed to away? Perfect. So what does toward tell me? Higher frequency. First thing you should decide. Did that get rid of two choices right away? Two other questions to consider. Is it reflected or one way? I.e., if it's reflected, it's going to be shifted once going there and shifted again coming back, so doubly shifted. But in this case, is it reflected or going one way? One way. It's going from the sender to the receiver. And then the last thing is the magnitude. So forgive me on this one because I'm going to do the math thoroughly and in the end come up with a shortcut. So here's the initial frequency, F naught, unshifted. This is the Doppler shifted one. Speed of the wave, plus or minus receiver, plus or minus giver. I'm going to not worry about the plus or minus conventions and just plug in what I need. I need the frequency to be higher, so I'm either going to add numerator or subtract from the denominator. So who is moving, the receiver or the sender? So what does this sentence say right away? When the receiver of sound is moving. So yeah, the receiver is moving. So I'm going to ignore the giver. That one's just going to go away altogether. And I'm going to add rather than subtract. So it's going to be a plus. It's going to turn into this equation. I'm now going to split this into two parts, V wave over V wave, V wave over receiver. What is V wave over V wave? Oh, you're welcome. 1, so that's gone. So 1 over this fraction. I'm now going to multiply this times 1 and this times that ratio. So this one's going to seem like a little bit of work, but F unshifted times 1 is F unshifted plus F unshifted times that fraction. I'm then going to subtract F unshifted from over that side. So F shifted minus F unshifted equals that. And that's your change in frequency. All that work to come up with this relationship. That's the one I truly care about. So the amount that the frequency is going to go up or down is simply going to be the original frequency times the ratio of how fast the person's moving compared to how fast the wave is moving. So in this case, they're moving at 34 and the speed of sound in air is around 340. What is 34 over 340? 0.1. What percent? 10%. Best answer? This. It just gave me a systematic way to do it. Number one, towards. Number two, mathematically approximate the magnitude of the change. Number three, decide whether it's one way or a round trip. Yep, so here's the thing. If the sender would have been moving, then it would have been subtracting here. It still would have been 1, but then it would have been a subtracted term instead of added term. I'm going to be okay with that. I'm going to now, I know the math isn't the exact same, so I'm doing the receiver, and I'm going to tell you we're going to do the same thing for the sender, either one that's moving. So that's going to be my shortcut. I'm just going to guess from this point on. Yes. So everybody see what Jonathan said? If we know that 34 and 340 are a ratio of 1/10 or 10/1, whatever, you see a factor of 10, then you're probably dealing with a 0.1 or a 10. So I'd go for that one. But if it's round trip, it might get a little tricky. Okay, so this question I don't care about as much as the next one, but we did 3 things: toward, one way, and we have a shortcut. So let's take what we learned in this question and apply it to this one. Cars drives away from a bird squawking with a frequency of 989 hertz. At 30 meters per second, people in the car detect the squawk frequency as. Okay, so what's the first thing I need to decide? Toward or away. Perfect. So this one is moving toward or away. This one's now moving away. So very first thing, decide toward or away. In this case, it's away, lower frequency, which means get rid of which answers, like you said? A and B are gone. Perfect. Second question, is it one way or an echo? One way. The bird is giving the sound, the people are hearing the sound. So it's going one way, which means I don't have to double anything. So one way, singly shifted, whatever value I get. Last but not least, what is the magnitude it's changed by? So 30 is the speed of the person moving. 989, what is that roughly equal to? One over 33, I'll go with that. I'm going to say around 3%. I'm going to say 30 over 1,000 or 3 over 100. Somebody agree maybe around 3%? Have I plugged the wrong numbers in? I haven't done it yet this lecture, so I needed to do one of these. What number should I have in the bottom of that one? .340. It's a speed ratio. So now what do I get? Well, now it's a little bit trickier. I'm going to say 3 over 34, as you mentioned. I know, damn it is right. And is it worth the time for me to make mistakes? It actually is. So when I screw up, hopefully I've done it for you. You don't have to in the future. So learn from my mistakes. So perfect. You're going to say this is around 9%. I'll go with that. How many agree it's less than a tenth? So what is 9% of that number? So 9% of 1,000, you're saying it's around 80 or 90. I'm going to say this is close to 1,000. This is a little under 9%, but close. So can I say it's around 90 hertz? So how much did the frequency drop by? Around 90. So 989 minus around 90 is around 900. How many can actually, that math is a little bit tricky, but how many can actually do that faster than before? How many can analyze toward or away, one way or echo, and estimate the magnitude? Notice the approximate here. If you did this in real physics, you would be wrong. You'd get things wrong, but because it's MCAT physics, this is a perfect way to do it. Yeah, good question. Where did the 340 come from? So somebody who put 340 in, why did you do it? Speed of sound in an air. How do you know it's in an air, Alec? I didn't tell you. The word air doesn't appear anywhere in that. I'm gonna assume it's a bird. So the conditions, perfect. So if they would have said dolphin like we did earlier, what was the number? 1500. For dolphin, 1500. For a train whistle, 340. For a car driving down the road, 340. So it's basically air is where that number came from. Okay, so far so good. So Doppler, I hope, is made more simple, or simpler at least for the MCAT. Again, if you're taking physics, you have to do it the legitimate way. If you're doing MCAT physics, this is going to get you a right answer every time. Okay, clicking in 3, 2, 1. Screenshot if you need. Waves on a string. I just can't remember what exactly this thing's called at this point, so I'm going to need your help. This is a point where I get no displacement. I'm not sure if I spelled displacement well, but what do you call the point where you get no displacement? What? You mean it's simple as no displacement is no not an antinode. An antinode is in the middle. So you have a node and a node, which means can the string move at that point? Nope, it can move in the middle. So I have an antinode. But just keep in mind then that when we have a stringed instrument, it must start and end with a node, meaning there's only so many allowed frequencies. These are what's known as harmonics. Harmonics, I think, are better understood by a physical experience than hearing them. How many have ever jumped up and down on a trampoline? Okay. Does it matter how you jump? Oh, you get too close to the side with those springs. Okay. So how many want to jump in phase? So how many would like to be at the lowest point? It shoots you up. You land at lowest point, shoots you up. Can you get higher and higher? Oh, so what's it mean by in phase? So if the trampoline is at lowest point and you're there, and then when the trampoline is at highest point, you're like, oh wait, your arms grew. So you're at the lowest point here, you spring up, you land down. So you keep on, as it goes up, you go up. As it goes down, you go down. So if you're in phase perfectly, can you jump higher and higher and higher? Sure. What happens if you're out of phase? I believe they call that knee injury. I believe they call that knees turn into chin. So how many agree you want to be perfectly in phase with the trampoline to get best results? But what if you could do this? What if while you jumped up in the air and came back down, what if it went up and down twice, but still was at its lowest point? So what if I could go up and come down and it went up and down twice? Would I still land at the right spot? Would I still land at a low point? Meaning I went up and down once, it went up and down twice, but I'm still landing in the perfect spot. Am I in phase or am I in phase with the second bounce now? You're in phase with the second bounce. What if I went up in the air and it went up and down 3 times? Would I be in phase or in phase with a third? Congratulations, you just told me about harmonics. Harmonics, you're in phase with the first one, in phase with the second one, in phase with the third one. That's what a harmonic is, where the event repeats itself and you happen to land at the second bounce or third bounce. So in theory, how many have ever dribbled a basketball by being perfectly in phase? You push the ball down, it all works out. But how many have ever done one of those speed dribbles where your frequency of your hand is going up and down twice when you hit the ball? Or how many have actually been out of rhythm, out of phase with the ball, and it bounces weird? So any sort of experience like this, if you're in phase, all is good. If you're out of phase, bad, but also in harmony. So when we're in harmony, we may not be perfectly in phase, but we're in phase with every second or every third. Okay, so here's what I'm curious about, and I want you to teach me some things about sound. I'm going to give you a specific example, and I'm going to worry about what's going on here in a second, but I think if I'm looking at the top view of a piano, here are the keys. I think the piano is shaped like this. I think that's the way it works, isn't it? Or do I have the enantiomeric piano? I know it's so weird, but even people who play piano have to stop and think about this sometimes. Have I drawn the top view of my piano correctly or incorrectly? How many are afraid to answer? I know it's weird because you've seen a piano a million and one times, but it's like, dang, can't remember for sure. Ends up piano isn't that way. The way you hopefully can remember which hand plays the longer notes, the deeper notes. Oh yeah, that's right, the square piano, that's what all of you have. But how many agree the left hand plays the bass notes, the right hand plays the higher pitch notes? Is that true? What creates deeper notes, longer or shorter strings? Longer equals lower pitch, shorter equals higher pitch, tight equals high pitch, loose equals lower pitch. So these wavelengths, oops, sorry, didn't mean to do that, I meant to say that these are the allowed ones. So this is half a wave. So the length of the string equals half a wave. So 2 times that string, take the string here and again, you get 1 wavelength. So wavelength equals 2L. Here, that's 1 wave, so the wavelength equals L. This is 1 wavelength here, so it's actually 1.5 wavelengths. How many learned this equation that 2L over N equals the wavelengths that are allowed on a string? I mean, I'm sure they mentioned that at some point, you memorized it and all's good. But we typically hear wavelengths or we hear frequencies. We hear frequencies. So I need to go and change this equation. So the frequency, and I can put an N subscript, meaning only certain allowed frequencies, whole numbers, will equal the speed over the wavelength, which equals speed over 2L over N. N comes up, and you get this equation. You get N on top, so N, the modal number, the harmonic number, times V, the speed of the wave on the string, divided by 2L. So here's my question. If I have longer strings, if L goes up, what happens to the frequency, according to that equation? It goes down. Perfect, exactly. So L goes up, frequency goes down. How many learned that if you tune a guitar and you tighten the string, the wave vibrates faster on the string, so V goes up, what happens to the frequency? As you tighten your strings, frequency goes up, perfect. So if you tighten your string, V goes up, causing the frequency to go up. And the way I want you to remember this, if you ever see a really nice violin, a beautiful guitar, a nice cello, whatever instrument, you sit there and you think, wow, that's so nice, I wish it was mine. Happens a lot. You can say you frequently envy their tool. You frequently envy their tool, their tool. But that's your equation. That's the one that matters for stringed instruments and open pipes, we'll look at in just a second. But how many are okay that, yeah, the deeper sounds are the longer strings, bass guitar, longer strings than rhythm guitar? The length and the tension are the two things we mess with. The last thing, if you've ever seen a cello or a bass guitar or a very large instrument, would you say those strings are typically thick or thin? Okay, thick, got 2 votes. What about a violin, thick or thin? Very thin. Where is thin in this equation? Where is thick in this equation? Thicker strings move slower, thin strings move faster. So it's in the numerator. It's part of the V, exactly. So hopefully this makes sense for a stringed instrument. Let me hang on to this equation. So I'm going to say, I frequently envy your tool, and say it applies also to pipes. Oh, I forgot to mention that if n equals 1, then it's V over 2L, so I can factor the n out. So all the frequencies are an even multiple. So if F1 is 100, then the frequencies would be 100, 200, 300, 400, 500, and so forth. It's always, every harmonic is a harmonic number times the so-called fundamental frequency, or F1. Okay. Pipes. So weird set of questions for you. I want you to be able to teach me a whole bunch of things here. Are your vocal cords strings or pipes? So your vocal cords, the chords themselves, they are strings. So just word to the wise. Whereas the ear, it's a pipe that the sound travels through, but ultimately does it strike fibers, those cilia? So is it also, our hearing is ultimately string based? So going back to that previous equation, I frequently envy your tool. The longer strings to the lower frequencies. Just cool little things. So if they apply to your ear, same thing holds. Okay. For the previous system, we had a node, antinode, node. For pipes, it goes the other way around. For whatever reason, they want to have it set up that way. You want to have an antinode at each end. So how much of a wave have I drawn? Half wave, full wave, quarter wave? Half a wave, exactly. So enters an antinode, exits an antinode, everything's fine. This is known as an open pipe, or if you learned it from an old professor, just an open pipe. So that's antinode at each end. If the wave happens to equal perfectly the length of the pipe, this is going to get louder. So how many have ever put like a toilet paper roll up against your ear and the world sounds totally different? I mean, anybody ever done this? Put a paper towel roll or a toilet paper roll, just the center cardboard piece. Anybody ever put that up to your ear and listen? Okay. How many have ever made your hand like a tube? So roll your fingers into look like a roll of toilet paper. If you put it against your ear, does the world sound different? Why? All the same sounds, the world didn't change. What changed? You put your hand, and from pinky to index finger was this long. That meant the waves naturally in your environment that were this length all got amplified and you heard more of them. If it went like this, that one also got amplified. So that pipe naturally will make certain sounds come across louder, more intense, because it amplifies them. So as long as they're the same length, kind of cool. So we're going to finish on that same note in a second. How much of a wave is this? Yeah, I know. The ocean was recorded in the seashell. I was going to bring that up. Everybody has that. But this is a full wave from top to bottom back to top. This one is going to be 1.5 waves. So it ends up, the pictures I'm drawing here, antinode to antinode, string was node to node, antinode to antinode, string was node to node. Is this the same thing? Half, full, 1.5? For an open pipe, did we just end up with the exact same frequencies, literally the exact same ones that we just had for the string? So all that matters, pipe or string, I don't care if it's the same at each end, open and open, or string is fixed and fixed, same phenomenon, same relationship. Nothing changes with that. Okay, how do I tune a wind instrument? So for somebody who's really good at playing a wind instrument, do they tighten the strings on their wind instrument or loosen the strings? Nope. Depending on what it is, do they move the reed further in or further out, the mouthpiece further in or further out? And for any of you who play a wind instrument, how many know that your lip position on the reed or the mouthpiece, by changing your lip position, reshaping your mouth even just a little bit, can you change the sound coming out of it? Is that how the really amazing players can actually modify their mouth shape and mouth position to, I guess, in a moment's notice, to get the right sound? Kind of cool. Last but not least, whenever you see an orchestra, do they tune and then start playing, or do they play for a while and then tune? Why do they play for a while? Bit build up. Okay, you want to see if it sounds weird, but you play for a while, then you tune it. If it sounds weird, you don't tune it right away. You keep playing until it's warmed up. The instrument has to be whatever playing temperature it's going to be at, because if it gets cold, does the air around it get cold? Does that actually change? Can that actually change the sound you hear? So an instrument that's tuned for room temperature may not be tuned in an air-conditioned room. Might be slightly off. Okay, last but not least, what is the difference between this pipe and this pipe? Looks the same on the left, but what about the right? It is closed. When you hit a wall, do you pass through or do you reflect back? Reflect back. The trick here, it wants to enter and exit an antinode, but it must reflect at a node for this to work. This wave must come in here, start at an antinode, reflect at a node, and come out if it's going to work. If it's going to enter at an antinode and exit an antinode, it must reflect at a node. How much of a wave have I drawn right here? Not a half. So if I followed through that part right there, I'd have to go back to the middle, back to the bottom. I'm now writing across my wall. You can't see this. But that right there is a quarter, 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 and then etc. It's only a quarter of the wave. So suddenly, instead of having a factor of 2 like I had here, now I have a factor of 4. The other thing that's sort of funky and weird on this one, I want you to just watch carefully. So this is one of those, just please zero in and watch this. If it enters at an antinode and reflects at a node, so if I did half a wave, then half a wave is going to look something like that. So if it comes in and reflects, it's going to reflect the same way it comes back. So if my in wave is like that, my out wave is like that. Let's see what happens. So if it comes in, reflects out. Is the wave coming in, what's it going to do when I add it to the wave going out? So that's the in, that's reflected. What happens when I add these two waves together? Let me draw this line here so it demonstrates where we are. Low point and high point, 0 and 0, low point and high point. When I add them together, what happens? They cancel. So here, the reflected wave is the anti-wave. How loud is something that it's been canceled out, destructive interference? No wave. How many learned that when you took physics that only odd numbers work, even numbers cancel? So does anybody remember that? That for a closed pipe that's closed on one end, you only can use 1, 3, 5. Does that sound at all familiar to anybody? If not, I'll just say, just know that random fact. When it's open at both ends or string fixed at both ends, I envy your 2L, anything can work. But when it's a pipe that's closed at one end, it's antinode reflects at a node, comes out an antinode, that one's allowed. Odd number allowed, even not allowed. Odd allowed, F4 not allowed. So note that only odd number, n must be odd. So you have that little caveat. So I want you to explain something to me. This is kind of one of those cool phenomena in life, but how many have ever filled up a glass of water? Has anybody in their life ever filled a glass of water in the sink? If it was totally dark, can you tell when it's full? Have any of you ever listened? How can you hear it? The water talks to you. Jonathan, you want to share something? Really, the water talks to you, huh? The pitch changes. How many have definitely heard the filling up of a glass kind of? How many have definitely heard that little whistling as it fills up? Why is that? Please explain to me why it would sound different. Is this an open or open closed pipe? This is an open closed pipe. It follows this right here. So as you're filling it, what is happening to L? As the water is getting higher and higher and higher, the L is now getting longer or shorter? Getting shorter. If L is going down, what's happening to the frequency? Frequency is going up. How many would agree you don't really notice it here? You really don't notice it until it gets higher and higher. And then once it goes here, you read a small change in the water level is actually a pretty big change in the relative length. So here I got to fill it up halfway to get it to change by double. But here I don't have to fill it up as much. It takes less and less to change the height drastically. So were you actually a physicist and didn't realize it when you were studying that, when you were listening, filling up the glass of water? So cool when these things can explain real life. So even if you didn't play an instrument, you filled a glass of water, you've seen a piano, hopefully these things are good for you. So one last thing I want to throw at you. So got to know pipes and strings. Want to ask you this. Which has a higher range of frequencies? Your vocal cords or your ears? Which has a greater range, what we can say or what we can hear? So from a practical standpoint, do we want to be able to only hear what people say, or do we want to be able to hear more than just spoken words? We want to be able to hear more. Also, from the other perspective, when I speak, do I want to speak a wide enough range where people don't understand? They can't hear me. No. So it ends up, your vocal range is about 1,000 hertz, whereas your hearing range is about 20,000 hertz. We hear a much wider range. So for vocal cords, we can't really generate that much. But one last thing to ask you, what happens as you get older? Do your vocal cords get longer and thicker? Yep, as you grow, your vocal cords get longer and thicker when, I guess, pre-pubescent and post-pubescent. Ah, perfect. So Michaela, explain to me, how are you seeing in this equation why your voice would get deeper? As they get longer, it doesn't get much longer, but a little bit longer. Degree length grows up, you grow a little bit, your larynx gets just a little bit bigger, and frequency is going to go down because length went up. But as they get thicker, they vibrate slower. V goes down, frequency goes down. So exactly. So is that what happens when somebody goes through puberty? That is that one of the things. Their vocal cords actually thicken, but they also lengthen ever so much. Yeah. And so that's why when you think of people who are really tall, you think of somebody with a deep voice or a high-pitched voice. So somebody's like 6'5", 6'10", something like that, typically deep because they have longer everything, bigger everything, including vocal cords. When somebody's like a kid, they're very short, very thin and high-pitched, short vocal cords. So hopefully this seems okay. And how many agree it's kind of cool when you can apply why the glass sounds the way it does, why tall and short, old or young sounds the way it does. Hopefully all this helps. Leading to one last thing to toss at you. Let me get rid of my pictures. 3, 2, 1. Only has to be an odd number. So screenshot if you want to. Oh, this stuff is so cool. When you apply it to real life and you realize, shit, I know this stuff. And how many have discovered that? If you know it in real life, it makes so much more sense. You pick it up so much faster. You relate to it so much better. By far, the more things you can connect to your real life experience, and physics actually does it pretty well, the better you'll know it. So if you can connect things, filling a glass of water, your vocal cords, those things, you'll do well. Leading to, oh my gosh, it's like a message. What's it say? Time for fun, time for frolicking, time for homework. Oh, and there's more to the message. Oh my gosh. Huh, what? Go do it later? Go do it now. Oh man. Like something overtook my computer and made those messages. I didn't do it. But anyway, hopefully this went well and you're feeling decent about this material. Oh, you're very welcome. Yeah, Doppler is one of the things that can be made really easy, multiple choice. Go sleep. That's right. You're pushing 9 something. So yeah, sorry, went a little bit over time. Starting late added to that. Thank you guys so much. Hopefully it makes the next lecture, I guess, next Tuesday go better. And then I'll probably switch Friday to nuclear based on like what the feedback has been, or forces. I'll probably do forces actually, because that's a natural sort of connection. Yeah. And sorry I haven't gotten back to you. I'm still matching up a schedule. Apparently, they still haven't sent me exactly when everything starts, but I think basically everything you sent, those days will work except for the 2 holiday ones. That's what it is. But I need to figure out exactly when my official data report, because school starts a certain day, but I forgot that all the friggin' in-service things might mess up that whole week. So, all righty. Well, I'm going to go ahead and exit out of this. Oh, shoot. No, sorry. Oh, no. I don't know if you guys can still hear me because I've lost many things right now. So sorry about that. There we go. Okay, so I'm back. Perfect. Okay, I'm going to stop that share. And I will see you guys, I guess, in a hop skip and tomorrow if you come to office hours. Have a wonderful night. Okay, I'm going to go ahead and hit the kill button. 3, 2, 1. Have a great night.